Okay, for this video, we've got two final topics to finish up our section, and one of them's kind of small, so I'm doing them together. The first is we want to talk about multicenter molecules and shape. So how do we deal with a molecule that looks like this? So let's say we had a hydrogen connected to a nitrogen, connected to a hydrogen, connected to a carbon, one pair on this. We have two hydrogens on this, and then we have carbon, we have a double bond to an oxygen, then another oxygen with two lone pairs, and a hydrogen. Now this is an example of a molecule that I would not expect you to get a Lewis structure from, in terms of I couldn't just hand you this and have you come up with this shape. Now, eventually as an organic chemist, you'll get to where you could do this. But for Gen Chem, there's no reason I could say, oh, you have 5 hydrogens, a nitrogen, 2 carbons, 2 oxygens, make the molecule. That's not reasonable. But what I can do is I can ask you, hey, if you have this molecule, what's its shape? So what you do is you treat it like a bunch of smaller problems, and you figure out each one individually. Or the question might even just ask you about one of them even. So for example, we start with this nitrogen here. So for this one, it's a center atom because it's connected to more than one, right? Like these hydrogens are only connected to one atom. Therefore, we're not going to call them center atoms. We don't have to worry about their shape. But this nitrogen here, you'll notice it has 4 electron groups. That's because there's 1 lone pair, 3 bonds, and it has 1 lone pair. So if we go back to the last video, if you have 4 electron groups and 1 lone pair, you are going to be trigonal pyramidal. And that means you'll have a bond angle of less than 109.5. But then we can keep going. This one, we have 4 electron groups, but no lone pairs. Therefore, it's, I don't know why I put dots on electron groups and not on lone pairs. There's no particular reason. You probably can't even see the dots on electron groups. Just however you want to label it. This is just for your own edification, whatever makes sense for you. So 4 electron groups, we said if there were no lone pairs, the molecular and electron geometries were the same. So this is going to be tetrahedral. For both its electron and its molecular. And it's going to have a bond angle of exactly 109.5 degrees. Now, here, this one we have 3 electron groups. Remember, the double bond counts as one group. So we have 3 electron groups, and again, we have no lone pairs. So that'll mean we have trigonal planar. And trigonal planar involves a 120 degree angle. So even though for the purpose of drawing this to make it easy to see, we put it so that these atoms, it looks like there's 2 90 degree angles and a 180 degree, but that's not true. The real molecule is a 120 degree shape. So these things should actually be bent a little bit. One thing about this though is usually when you draw this shape the first time, you don't yet know what all the angles are because you haven't counted everything and figured out the geometries. If you want to make this molecule more accurate, you will draw these with 120 degree angles, not 90 and 180. So now let's get to this oxygen here. We'll switch colors because that pen's starting to die. So we have 4 electron groups. We have 2 lone pairs. That means we have a bent molecule with less than 109.5 degrees. So this molecule that has 4 different central atoms ends up with 4 different shapes that make it up. So I could ask you, what's the shape of the nitrogen on this molecule? And then you wouldn't have to do the rest of this work. Or I could say, what are the shapes of the 2 carbons? Well, then you've got to figure out one is tetrahedral, one is trigonal planar. We could also ask a question like, how many of these atoms, central atoms, have 120 degree angles as their bond angles? Just 1. How many of these have angles of approximately 109.5? 3. Because that's a good way for me to ask. It's close to 109.5. This is not approximately 109.5 because it's 120. So, but these are just a little bit less than 109.5. So they would count as approximately. Or if I wanted right at 109.5, I'd just get this one here because these two would be different than that. I will make sure in your questions it is clear if I want exactly 109.5 or if I'm okay with these less thans. I think it's always important in those questions. It shouldn't be you didn't know what I was asking. It should be, oh, I didn't remember that if you had a problem there. Or I didn't realize some concept I needed to learn. So this is how we'll deal with multicenter atoms. You won't have to do the Lewis structure from scratch, but if I provide it to you, you should be able to tell me bond angles, you should be able to tell me shape names, both the molecular and the electron geometry. And while it sounds like a lot, remember that electron geometries are just a subset of molecular geometries, since the electron geometry and molecular geometry are the same when they have no lone pairs on the middle atom. So if you learn all the molecular geometries, you know the electron geometries as well. Just make sure you keep them different so we can ask the question, no, what's the electron geometry? And you can answer that too. And just to point out, sometimes we're more concerned where the electrons are, sometimes we're more concerned where the atoms are. That's why we have two different names for something rather than just to be annoying. Although I know chemistry feels like that sometimes. So that's our multi-center atoms. So you should be able to work out, use the same concepts we learned for Vesper, but when we've got multiple atoms. Now, polarity is a concept that I think the base idea sounds really reasonable, and as you work on it, depending on how comfortable you are with geometry from math, it either feels kind of easy or really hard and unreasonable. And some people, I'm sure it's in between, but for me, it started out really hard, and over time, I just practiced it a lot, and this idea comes back up. We use it in 1212. The first exam in 1212, you will have a chapter that deals with polarity a lot, and organic chemistry work with it a lot. We're really concerned about whether something's organic or not, whether it's polar or nonpolar, because it helps us figure out things like, oh, which of these functions is a solvent? And that's important if I want to do a chemical reaction inside of a solution. I'd like to know if I make this nonpolar, then it can mix with other nonpolar things. You probably heard the term like dissolves like. So we worry a lot about how polar things are. It tells us things about chemical properties and what we should do. And not just chemists use that, biologists will be very relevant to that as well. We worry a lot about things like parts of cells, what's hydrophobic, what's hydrophilic, which is related to this polarity idea. Things that like water is very polar, as we'll see in a moment, whereas other things that are nonpolar are very not water-like. So it's not just chemistry, but ends up being in the other sciences as well. We worry a lot about this question of polarity. We introduce it here because it is so central, but I do think it's something you'll have to get over time. And I'm sorry, I got fuzzy again. I don't understand my autofocus. I will try to get it. I'm just going to stop for a second. Figure out where I am, camera. It's trying. It's best. There we go. I'll figure that out. I'm working on it. Did it again. I'm trying not to move too much. I am working on improving the setup. I've got a new camera coming. It will be here soonish. And I promise not to write on the board while I'm a blurry mess. And I'm sorry for wasting your time. Please figure this out, camera. Or I will have to make two separate videos, one for this and one for polarity. If I get closer, do you figure me out? I'm going to try the other side. Can you figure out where I am now, camera? Please don't make me stop this. I'm too tired right now to do a bunch of editing. Okay. I'm trying. Let's see. Try this. Does that fix it? Okay. I think that fixed it. There we go. I should have changed the setting. So now we're back to actually talking about things instead of the distraction of focus problems. So let's talk about polarity. So what this means, we take a molecule, like I forgot that was my dying flash. My HCl. So HCl, as a molecule, we know that chlorine is much more electronegative than hydrogen. What that means is the more electronegative atom is better at pulling electrons towards itself. Remember, we drew a symbol that looked like this, where this side is a partially positive side and this side is a partially negative side. If you have a molecule where there's a net charge, where one side is more negative than the other, we say it's polar. So polar molecules are going to be one. That means there's a net difference in what we call in dipole moment. So let's talk about it. So dipole moment is just this thing down here. That one side is more negative and one is more positive. This is something we can measure. So we can take a molecule. There's some techniques we can use to actually measure how much difference, like where the electrons spend more time. So it's important, the reason we say net is because in a lot of cases you have more than two atoms. With two atoms it's easier. Just look at electronegativity difference. This chlorine's more electronegative, pulls on the atoms, makes it polar. Let's look at a case where it's a little bit less clear. So, for a polar molecule, let's look at CO2. So CO2. Oxygen is more electronegative than carbon. That means we end up with a shape that looks like that. For one carbon-oxygen bond, we get a partial positive and a partial negative. So by itself, you might go, oh, of course. Okay, so of course, if this is a partial negative and this is a partial positive, that looks polar. And by itself, this bond is a polar bond. But what's important is it's not by itself. So this carbon-oxygen, oh, it does the same thing, but in the opposite direction. So when they play a tug of war, nobody wins because the oxygen is the same atom on both sides, They're both pulling on the electrons going, I want you, no, I want you. And they both take them away from the carbon, but they're able to equally balance out because they both pull equally hard because they're in opposite directions from each other. This is why we had to do all that shape stuff. We had to know this formed a line. Two opposites of a line can pull on each other, and lo and behold, we end up with a nonpolar molecule. Now, on the other hand, I'll make sure, I'm used to being on the other side, but for the camera, I'm doing this time, so I'll try not to block the board. So let's say we take water. We said that water had a bench shape. So what's important about that is even though here you might think, oh, so oxygen's more electronegative, that means the electrons are going to go towards the oxygen. Well, something to notice here is even though there are 3 atoms in both of these, they're not oriented the same way. This is a bench structure. So both of these arrows point in the same direction. They don't cancel each other out. So both of them point towards the oxygen. This means there's a net negative charge on the oxygen, a net positive charge on the hydrogen. So what you have to do with your molecule is you have to look at it and see, do things balance out? Like in the carbon dioxide case, sorry. So if they're both equally pull in all the directions, they'll cancel each other out. Whereas somewhere like here, you're going to get an unbalanced setup where you end up with a net negative charge on it. So that means this oxygen is partially negative, hydrogen is partially positive. We end up with a polar molecule. So this is hard to work at at first, but I'm going to have some tips that can help you out. So step 1 is going to be, well, I'm just going to go over these. They're not. So first, rule 1. It's not explicitly a rule. These are like tips and tricks to try to help you do this more easily. Learning how to look at geometry shapes is the best answer actually, and looking at pictures of them. But I know sometimes practically that can be hard. So these are some things to help you as you get started. So all of the electron geometries you learned, those were about, or you're still learning, same week, they're about separating the electrons as much as possible from each other. What that means, even if there are polar bonds in our shape that our electron geometries predict, for example, tetrahedral. Let's take as an example. Let's take CF4. So if we see CF4, the first thought might be, well, fluorine's more electronegative, and there's 4 of those, but they don't look like they're in the same direction to me necessarily. Well, they do look like it to me, but I understand as a student, this does not initially look like it's necessarily symmetrical. What's important is all of those electron geometry shapes that have no lone pairs, they are set up in such a way that they are all symmetrical. That's why they're equally spread apart, because the electrons repelled each other in the furthest away directions. That's what made those the actual shapes the molecules take. So what that means, if all of these atoms are the same, in any of our shapes from our electron geometries, so the ones that don't have any lone pairs, it's going to be nonpolar, even with polar bonds. So this is nonpolar. And that'll work for all those shapes. And that helps for a lot of them. Now, you may notice that means you're going to need lone pairs on your central atom to end up with polar molecular shapes. And in the majority of cases, that will get you there. However, there are some shapes where we end up with things where you would think where there are lone pairs, but they end up being nonpolar. So I'm going to give an example from the ones we looked at in the molecular geometry section, just to show how they come up. It's going to be with either the 5 electron or 6 electron group shapes, because we start having things on the tops and on the sides that are able to balance each other out. So let's take the molecule, again, XeF4. So here we have a xenon in the middle, and you've got 4 fluorines here. Now, there are going to be some lone pairs, and we just said, oh, lone pairs tend to make for a polar molecule. The issue is these 2 lone pairs are exactly opposite each other. One's on top, one's on bottom. Any effect that this one has on polarity related to these is going to be the same as this. So these 4 fluorines are separated as far as possible, and they're exactly opposite each other. And I think this shape is nice for seeing that because it's a square. If it's a square, then they're all going to pull, and then they all are still equal to each other. So this still ends up being nonpolar, even with those bonds, even with the lone pairs. Another example was something other than xenon. I'm having to count electrons in my head. Does IF2- work? 7, 14, 21, 22, 8, 16. Yeah, we're going to do IF2- to show you an example that doesn't have that. So IF2-, just as good practice, Iodine has 1, so that gives me 7 electrons. Fluorine, there's 2 of them. They each have 7. That's 14 more. And then we have to add 1 electron for the negative charge. So this ends up with 22 electrons. So if I get this, when I draw it, I'm going to end up with 3 lone pairs. So I do my iodine. So first I'm just going to draw it as a Lewis structure without worrying about shape. I'm just going to put the fluorines here, because you wouldn't necessarily know the shape when you're first doing a Lewis structure. So that uses up 4. Yeah, I'm definitely going to fix the camera for my next video so I can be on the left again. I'm blocking this a lot. I'm trying my best not to. So we have 18. So 2, 4, 6, 8, 10, 12. That uses up 12. You get 6 more. Yeah, camera, there, 6 more. So we have 1, 2, 3, 4, 5, 6. So, and it's got a minus charge. So now if I instead draw that in its actual shape, we have an iodine in the middle, we have 2 fluorines on top, and we have our 3 lone pairs around the middle. So again, these are the only 2 other atoms, and even if they're pulling on the electrons opposite each other, these 3 lone pairs are all able to balance each other out. So even though you end up with lone pairs, this ends up as a nonpolar molecule. Now, I will point out that I looked at specifically the examples that were nonpolar. The majority of cases with lone pairs on your central atom will usually end up being polar. So just to do one real quick, let's look at NH3. So if you have a nitrogen with 3 hydrogens, we can see that however you end up drawing, we know that nitrogen and hydrogen, that by itself is a polar bond. So if nitrogen and hydrogen have different electronegativities, we end up with a polar bond, but all 3 of the nitrogen and hydrogen bonds are going down. They form a tripod. Nothing is going up. So if we have if more of the negative charge builds up on the nitrogen, it's going to build up towards this nitrogen, and it'll be partially negative, whereas this down here will be partially positive. So we end up with a polar molecule. And this is what happens in most cases. And I'll be the first to say that I think when we first discussed polarity, it's a topic that's so critical to chemistry that we bring it up here. But I do think it's hard for people, especially if you have some trouble with the geometries. And by that, I don't mean memorizing a bunch of names. That part's not hard. But it is difficult to test you directly on how well do you know the shape. Because I'll admit, we don't want to try to grade your ability to draw this shape. Plus, the drawings aren't really the same as what it really visually looks like. There are best choices. But I know as a student, I was faster at being able to draw the shape on paper exactly like the teacher did than I was at actually getting the shape idea in my head. This is why things like model kits work really well. It's why in organic chemistry we're going to encourage you to get your own model kits. You can literally build these molecules. It's why now that you have the internet, it's nice to look at the shapes there. They can give you more of a feel for what these things look like. But I'll be the first to say that I know trying to figure out which are polar and nonpolar can be challenging at first. But it is useful. In addition to coming up inside of this class, the very first 1212 chapter is about polar solvents and nonpolar solvents and having to know the difference between them. So I promise this won't just disappear. I can't go, man, I don't like polarity. Maybe if I just ignore it, it'll go away. It won't. It will come back. Again, we'll review it there, or whoever your professor is will, and it'll come back up again in organic even more. Now, each time we'll try to learn more about it, we'll give you more information, you'll be more engaged in chemistry as you get further along, it gets easier to work with. And then if you go off to biology, you'll worry about it too because of things like how cell membranes work in other areas. There's a bunch of places where you worry about, wait, is this polar or nonpolar? Because it determines a bunch of stuff about different molecular shapes. Things like, what shape does my protein take? We worry a lot about polarity. So there are a lot of questions in other fields as well. It's not just well, I don't like chemistry. I'm going to try to ignore this polarity thing because it's kind of icky. So we do care about it. It will come back. So with that, I hope this is okay. And this is going to be the end of this chapter. And then the next chapter we're going through is going to be kind of short. We're only doing a little bit in the next chapter.